Hey everyone, this side Ankush Rana. I'm currently pursuing my BSc Honours Electronics from Acharya Narendra College, University of Delhi. I, on behalf of Department of Electronics, present a tutorial on to design and obtain the frequency response for the first order active Butterworth high pass filter having the upper cutoff frequency FC in Hertz using IC 741. I would like to thank our Professor Amit Garg and Dr. Ravneet Kaur for providing me such an opportunity. So let's begin with this virtual lab. So I have divided this virtual lab in mainly 5 parts. First, we will be covering the theoretical concept, which will cover the basics of op-amp and the high-pass filter. Then we will be doing the working formula and the basic work. Here we will be discussing about the basic working formula and the voltage gain equation. Then we will be looking at the multisim setup, where we will design the circuit and look at the circuital component use. Then we will have an observational table and graph, in which we will be plotting the graph using MX Excel, and I will just let you see the readings which I have observed in the practical when I have done this practically and the lab, and then we will talk about the results and observation at the end of the session, and we'll discuss a little bit about the role of factor. Talking about the theoretical concepts, so let's begin with it. A little bit basics about op-amp. So here you can see the op-amp IC, which is 741. Here op-amp IC 741 is nothing but a monolithic integrated circuit which comprises of a general purpose operational amplifier. It was first manufactured by Fairchild Semiconductor in the year 1963. The number 741 indicates that this operational amplifier IC has 7 functional pins, 4 pins capable of taking input and 1 output pin. So this IC 741 op-amp can provide high voltage gain and can be operated over a wide range of voltages, which make it the best choice for use in integrator, summing amplifier and general feedback application. It is also featured short circuit protection and has an internal frequency compensator circuit built in it. The operational amplifier IC comes in 8-pin DIP package. So let's have a gist of little bit explanation. So I have discussed earlier that high pass filter is a circuit that attenuates all the signal below a specified cutoff frequency denoted by RL, or you can see it can be denoted by FC. So it is basically FL, or in some books you will see it is represented as FC. So thus high pass filter performs the opposite function of that of the low pass filter. If you are familiar with low pass filter, it will be the easy one to just go through the functioning of the high pass filter. Hence the first order high pass Butterworth filter circuit can be obtained by interchanging the frequency determining resistance and capacitor in the low pass filter. So high pass filter and the low pass filter go hand in hand, and it will be easy for you if you know one of the circuits. So here we have the circuital diagram of high pass filter. So here we have R1, which is connected to the inverting terminal, and it has one RF feedback resistor here, and this this op-amp is connected with the plus VCC and minus VEE, and it has an output which is represented by VO, and its non-inverting terminal is connected with the variable resistor R, and it's connected further with the capacitor, and that capacitor is taking input voltage input, AC voltage in. So let's begin with the working formula which will be required in order to complete this virtual lab. So here we have the formula VO is equal to AF B in J F divided by FL divided by 1 plus J F divided by FL, where FL, which we know is in cutoff frequency, is given by 1 by 2 pi RC. So usually we see in the practicals that C is fixed and its value ranges from 0.01 microfarad to 0.01, basically 0.01 to 0.01, its value ranges. So we usually keep this C value constant, and this R value can be changed because we have n number of resistors. So accordingly we can select the frequency which is required for us. And this is AF is nothing but the gain of an op-amp in band pass, and its value is given by 1 plus RF divided by R1, where Vin is nothing but the input at voltage at the input terminal. So here we have another formula. We have just put the cross multiply and put the VO divided by Vin, which is nothing but the gain which we will get, and it's equal to AF into F divided by FL divided by under root 1 plus F divided by FL to whole square. So this is the behavior of the high pass filter which can be observed from the above equation. So like at the cutoff frequency lower than, so if you are supplying frequency lower than the cutoff frequency, so the gain will be AF, so that gain which we will receive VO divided by Vin will be less than AF. And when the cutoff frequency at F equal to cutoff frequency, it should be F equal to cutoff frequency, which means that F equal to F dash L, we will have the gain equal to 0.707 times of AF, that is 3 dB down from the level of AF. And when we have the frequency which is greater than cutoff frequency, that is higher frequencies, the one can be neglected as in F divided by FL from the denominator, and the voltage gain which we receive is approximately equal to AF, which is constant. So let's look at the graphical observation which we must obtain. This is an ideal graphical observation which we should get. So here we have the frequency on the x-axis and voltage gain on the y-axis, and here you can see we have divided it into two range. One is the stop band, another one is the pass band. When the frequency is lower than the cutoff frequency, then it is known as the stop band, and when the frequency is greater than the cutoff frequency, then we get the band pass filter, basically the band pass. And here you can see the transition from here to till the FL. This slope is at plus 20 dB per decade, which is nothing but the roll-off factor, which we will be looking at the end of the session, what the error and the difference which I have received when I was doing the practical. And here we have AF, which is the constant gain, and here we have the cutoff frequency. At cutoff frequency the gain is 0.707 times of AF, and it is also known as 3 dB down. So that's all about the graphical observation. So let's look at the multi-sim setup. So let me just shift the window to the multi-sim setup. So here I have already designed the circuit in order to save the time. So you can design this circuit on your own. It is very easy to implement this circuit in multisim. Now let me just quickly go through the settings so that it is easy for you to change the setting in the multisync. So here you can see that at output is at this 3 node, and the input voltage is at 5. So we will go to AC sweep. Just clicking on the AC sweep, you just need to change this value. We can keep the starting value from 0. We are starting the frequency from 0, and we will go to till 5 kilohertz. That totally depends on you, but for this practical I am keeping the maximum range, or the stop frequency range will be the 5 kilohertz. And the sweep type, you need to keep it linear, and the maximum point I have kept 150, and the vertical scale also I have kept it linear. Then at the output you need to put this equation according to your circuit. So we are interested in calculating the gain, so I have added an expression which is V out divided by V in. So 3 is basically my voltage, output voltage, and here V in is given through this 5 node. So I have written that expression accordingly. You can just use in case it is not available there, you can remove this and add expression as per your convenience and as per your circuit. After that you can keep this thing as it is. So let's quickly run this and see, look at the observation. So here you can see we have received 2 graphs. So we are interested in magnitude graph, not in the phase graph. So we can simply click right click and click on delete graph. After that you can see that we have received this graph, and you can just go through this graph, which is pretty much similar to the ideal graph, but when you will do this practical in the lab, obviously you will see slight difference, but the basic ideology will be almost similar. So I hope you are clear with this graph, and you can see it ranges from 0 kilohertz to 6 kilohertz, but we have kept it till we are taking the readings till 5 kilohertz, and at the cutoff frequency, which is 0.70, which is around here, we will be getting the cutoff frequency at 1 kilohertz around. You can see it is around 1 kilohertz frequency. So I hope you're clear with this graph. Then after the multisim setup, we will look at the observation table and the graph. So let's quickly jump to it. So I have already made the observational graph, so you can just go through the readings. Here we have just put it the serial numbers, input frequency which you will give, the output voltage which you will receive. Then we will be calculating the gain magnitude, which is nothing but dividing the output voltage divided by the input voltage. And then we will be calculating the magnitude, which is in dB, and it is given by 20 log 10 V out divided by V in. So I have made this observational table for input voltage 1 volt peak to peak, which is fixed, and here is the observation which I have received, and I have calculated the roll-off factor between these two values, which is at 6 and 8, and the cutoff frequency is calculated around here. So this is all about the observation table. Let me just quickly give you a little bit glance of the graph which I have received from the values. So this is the practical which I have performed in the lab, and here you can see the graph which I have received. Obviously there are some sources, there must be present some sources of error. but we are getting the graph very much similar to the graph which we have received in the multisim result. You can clearly see the same pattern we are receiving here, and that's all about the graphical representation. And this is about the cutoff frequency. Theoretical cutoff frequency which we here required was around 2.85 kilohertz, but the experimental is 3 kilohertz. So the relative error which we have found in the cutoff frequency is 5.26, which is pretty much good enough, right? You obviously see some errors while you are performing it in the offline mode. So here we have calculated the roll off factor. The basic roll off theoretical value should be around the 20 dB per decade, but the experimental value which we have received is around 21.23, which is pretty much close to the theoretical value, and the relative value which we have received in the roll off factor is 6.15. So that was all about the observation table and the graph which we have seen here. Now next, talking about the results and observation. So we will finally conclude that the frequency response is plotted on the semi logged graph paper, and the theoretical and the practical value cutoff frequency calculated are 2.85 kilohertz and 3 kilohertz. So these are the respective values which we have received for the theoretical calculation and for the practical one. The theoretical and the practical roll off factors in dB per decay are that is 20 dB per decay, which is for the theoretical value, and the practical value which we have received is 21.23 dB per decay, which is pretty much close to each other. Next, talking about the references which I have used. I have used the website Electronic Hub, and then I have used first order. I have find it out the content related to first order high pass filter on the eeeguide.com, and I have also used the reference books which named as Op-Amp and Linear Integrated Circuit by Ramakant A. Gaikwad. I would like to thank you all for watching this video so patiently. Thank you so much.